Hey guys, today we are starting our unit on fluids. We're going to pair fluids and thermodynamics together for one unit. It's going to be chapters 12 and 13 out of the book. Fluids is actually chapter 13, but we're going to do it first because I like it better. So let's move right on into it. First thing is the definition of a fluid. A fluid is defined as a substance that flows. There are two states of matter that we're going to look at that are fluids, both liquids and gases. Gases are also considered fluids, even though you don't traditionally think of them as such. One key difference between gases and liquids, obviously, besides the motion of the molecules that you already know about, is their compressibility. And compressibility is, the property of an object that makes it able to be condensed, compressed, squished into a smaller space. So gases are compressible. You can change their volume without changing the number of molecules physically there. Liquids are not compressible. They cannot get smaller or larger with the same number of molecules. Their volume doesn't change. And this is somewhat untrue. There's like hydraulic fluids that are specifically used for their compressibility, but the liquids we're going to be dealing with in a class of this scope are going to be incompressible. You can't squish them down. All right, the first big kind of major thing here, which we're going to mostly push past because you already know it, is density. Density is the ratio of mass to volume. The only major change that we have to density for this class is that density is going to be represented by this Greek letter rho, which looks like a lowercase p. At least the way I draw p's is I draw the stem and I draw the little loop besides that. But rhos, however, are kind of more tilted, and you draw from the bottom and go around. So when you're doing your handwriting, it's actually not that difficult to see a difference between a P and a rho if you do it in handwriting that way. So we use rho for density. That's going to be used pretty much everywhere else in physics. If you're doing actual physics, if you're doing baby physics, we'll use D because people can't remember density is rho. But you're semi-adults now, you can remember density is rho. And that is mass over volume. The units are going to be kilograms for mass. Volume is meters cubed. So the unit for density is obviously kilograms over meters cubed. Most often, the only issue people run into with density is figuring out the correct units. An example of this here would be finding the mass of air in a living room with these dimensions. I'm going to leave this to you. You can pause the video and try to do it. I'll write out the solution, and you can hit play whenever you think you've got it. See if you got it right. All right, you should end up here with a mass of 72 kilograms after finding the volume from the dimensions listed. Hopefully that's an easy process. If you can't do density at this point, that's pretty bad. But if you can't do density, feel free to ask me for help. All right, but today's main topic is pressure. Pressure is going to use density in it, so we have to cover it. But the main idea that we're going to be looking at today is pressure. Pressure is defined as F over A, which is force over an area. And liquids, or any fluid, is going to exert forces on the container that is holding them. The force divided by the surface area of that container is what's called the pressure. But the more subtle thing about pressure is that it is existent everywhere in the fluid. So way back in the beginning of this class, we talked about fields and how you can have scalar fields, vector fields, and a field is just, every point in space having a specific value, and the field is the set of all of those values. Well, pressure is similar. There is a pressure value everywhere within a liquid, not just where it's touching the container. That pressure is existent everywhere inside the liquid. And most of today is going to be spent on figuring out what numerical value that pressure is. Before we go into that, there's a few convention things / bookkeeping things that you're going to need to know. One of them is atmospheric pressure. So the air around you in the atmosphere is a fluid, and it has a certain pressure. At sea level, most places, This pressure is 1 atm, which stands for 1 atmosphere, 1 atm. However, there are a ridiculous amount of potential units for pressure. And these actually get used fairly frequently. 1 atm gets used in both chemistry and physics a lot. So does millimeters of mercury, mostly because that's the reading you'll get from a barometer. Torr is used often in weather, though torr is the same thing as millimeters mercury, mmHg. Pascals, PA, is the SI unit, so that one's going to be the one we actually use in this class is pascals, though you will also see atmospheres. 1 Pascal equals 1 Newton for force over meter squared for area. That is 1 Pascal. The atmospheric pressure of 1 atmosphere is 101,325 pascals. There is the unit bar, which is a Pascal divided by 100,000. So, that's cool. And then lastly, there's PSI, because we're in America and we got to be weird. And you see PSI everywhere in the U.S. You've got tire pressure for anything that you're using is going to be pretty much in PSI if it's like a physical object in the U.S. But the SI unit that you need to use for this class, the standard unit, is going to be the Pascal, which is abbreviated as PA and is defined as 1 Newton divided by 1 meter squared. The other thing is this difference in types of pressure. There's 2 types of pressure. Absolute pressure is the pressure that you would find if you really did force over area for pressure. That's the absolute pressure. The gauge pressure is defined as the absolute pressure minus the atmospheric pressure. And the reason gauge pressure is used is because it kind of offsets your readings if you're taking a physical reading with a gauge. So most places in the world, pressure values are pretty small compared to the atmospheric pressure. So in order to offset that crazy large number added by the atmospheres, you just subtract it back out, and that tells you the gauge pressure. But that atmospheric pressure is still technically at play there. But if we wanted to look at a system more closely, and you were actually taking physical readings, you'd want to find the gauge pressure instead of the absolute pressure. But really all you got to know is gauge pressure equals absolute minus atmospheric. All right, and this slide here has a lot of information on it. I'm going to make it smaller, and I'm just going to talk you through what it's saying. This is actually a derivation for an equation, and it's going to take a little bit of time, but I'm going to talk you all the way through it. But first, got to make this small over here in the corner so I got room. All right, so ignore everything that's on the slide for a second, and imagine that you have a cup of water. This is your cup. Here's your water level. Let's see, I can even make it nice and blue. All right, cool. Cup of water. Now, think back to your classical mechanics days from AP1. And think about the forces that you would have on this water. You should remember that every force on the earth has gravity pulling down on it, mg. Okay? It has mg, and then it also has a normal force holding it up so your water's not falling to the center of the earth. It's held by the cup. So the bottom of the cup is exerting a normal force on the water. But there is also a third force that is present on Earth because you've got air molecules floating around up here that have 1 atmosphere of pressure. So all of those air molecules are at 1 atm, which is like 1 times 10 to the 5th pascals-ish. But the value here is not important. We're just going to call that the pressure of air. And the pressure of air equals a force over an area. And this air is sitting on top of your cup. Your cup at the top has a certain surface area. So the top surface of this water, we'll give it an area of A. The force exerted on the top of that by the air, it's going to be force of the air, equals pressure of the air times the area where the air is touching the water. And if your water is just chilling there in glass, you should know that the sum of forces has to equal 0 because everything is going to be balanced out. All this just comes from considering forces like you would in mechanics on a box or something. It doesn't matter that it's a fluid rather than a solid. So now what you're going to do is you're going to define a coordinate system and add these forces up. We're going to say up is positive, down is negative. The force pointing up is Fn. You don't really know anything about Fn other than it's the force that's supporting the water. And going down, you've got mg minus mg. You also have the force from the air, which we said is the pressure from the air times the area, the surface area at the top of the cup. So that's a minus P of air times A equals 0. So you can rearrange this equation to find the normal force. You say normal force equals mg plus pressure of the air times the area. Now you might ask yourself, why are we doing this? And our goal here is going to be to find the pressure at the bottom of the cup. And we know pressure is force over area. So if we find the force on the bottom of the cup, which would be the normal force, or equivalent to the normal force, we could divide that by the area of the bottom of the cup, and we would get the pressure at the bottom of the cup. So we're going to substitute in for this normal force, that is the pressure at the bottom times the area of the bottom of the cup, which we'll say the cup is cylindrical, so the area at the top of the liquid is the same as the area at the bottom of the liquid. And that equals our same mg plus pressure of the air times area of the cup, which is a cool equation, but we're going to have to take it a few steps further. And I'm going to have to go to the next slide to do that. So our result from the last slide was that pressure at the bottom times the area equaled, let's see, what was it? mg plus the pressure of air times the area at the top. Now, if we're looking for straight up pressure at the bottom, we could divide this by A to get that pressure. So let's do that. Divide by A, divide by A, divide by A. Because remember, you got to divide by A everywhere. So those cancel out. You get pressure at the bottom equals mg over A, plus those A's cancel out. You get the pressure of the air, which is cool. But we've got this term in here, mg over A, that we got to deal with. Now let's look at it over here on the side, mg over A. So something we could do here is work with this m. And we're going to solve for this m from the density equation. You'll see why we're going to do this in a minute. So you take the density equation, density equals mass over volume. You solve that for m, you get m equals rho v. And we're going to plug that back in for m. So mg over A is going to become rho times the volume times g divided by A. Now, something cool here is that in a prismatic or cylindrical shaped container, volume equals the base surface area, which is A, times the height of the thing. So we're going to use that for V. We're going to say this is equal to rho AHG over A, which makes the A's cancel, and you get that mg over A equals rho HG, which we can exchange for this term right up here. Let's see, I need to erase to make some room. I'm going to get rid of that for a second. Okay, so we're going to plug this in for mg over A. We get that the pressure at the bottom of the cup equals rho, which is the density of the liquid, times the height of the cup, times g, plus pressure of the air. Now, we're going to actually generalize this equation even further because we want to know the pressure of a liquid at any point in the liquid. And to do that, I'm actually going to need to go to yet another slide. So our result from the last slide was that pressure at the bottom of the cup equals the pressure of air plus rho GH. And I think we may have had these two terms switched, but commutative property of addition, so it doesn't really matter. All right. And that only tells us the pressure at the bottom of a cup. But let's imagine the cup again. Cup of water right here. Here's the water. I'll make it blue. There's your cup of water. So your fluid here is really just a bunch of molecules put together. And when we considered it at first, we considered it one continuous object. We were just looking at this fluid. But you could call it two objects with a line splitting in the middle. You could say this is the top, this is the bottom, and you could consider them separately but making contact at that middle point. That's a perfectly fine thing to do mentally, is to just separate that into two separate objects that you're considering as a system. And if you consider the forces on those objects, they're the same forces as we had before. Let's look at the top object. It still has an mg going down. It has an Fn going up, though this Fn is created at this surface, so that's the normal force from the bottom half of the liquid. And you also have the force of the air going down, which are the same three forces we had before, so the same equations are still valid. This equation right here is still valid. But now, instead of being at the bottom of the cup, we're at this point midway through the liquid. So the pressure there, we could say, is the pressure at the bottom. We're just going to generalize that to be pressure. P at any point equals the pressure of the air plus rho G. But now, instead of using the height of the cup, we're just using the height of the section that we are looking at. And the height of that section is called the depth, which we will denote as a D. So the pressure at any point in a liquid is equal to the pressure of air plus rho GD. But we can generalize this a slight bit even further and say that pressure equals the pressure at the top, which could be the air, it could be from something else. We're just going to call that pressure naught. So this force that's pushing down from air in our picture could be from something else, so it could be a different pressure, but it's pressure naught plus rho GD. And this is the equation for hydrostatic pressure, which we're going to use very consistently from now on. You can go ahead and use that to solve this problem about a submarine. It's very much plug and play. So pause the video, try to do it on your own. I'm going to write down the answers. All right, and you should get an answer of 3.13 times 10 to the 6 pascals, which is also 31.28 atmospheres. All right, we still got a couple more principles to look at with pressure. The first one is that if you're filling up a system of containers where you're using the same liquid everywhere and everything is connected, the water or the fluid, whatever it is going to rise to the same height everywhere. So across each part of the container, it's going to end up either filling that part or going to the same height. And a consequence of this is that at a given height in the system, in the container, the pressure is the same across both points. So over here on drawing B, the pressure at points 1 and 2, since they are on the same horizontal line, are the exact same. Now we can use this idea for quite a bit of problem solving. Let's look at this question here. It says water fills the tube shown in the figure. What is the pressure at the top of the closed tube, which is right here? Got to find the pressure at that point. So our strategy here is going to be to say this point right here is going to have the same pressure as over here because they lie along this same line. So if we find the pressure at this point, we found the pressure at the top of the closed tube over there. And that's pretty easy to find. We know if this isn't air, that it's got a pressure sub-zero of 1 atm, which is 1 times 10 to the 5th pascals, right there at the top here. And we know that this depth is 100 centimeters minus 40 centimeters, which is 60 centimeters or 0.6 meters. And it's very easy to find the pressure at that depth. You just say pressure equals the pressure naught, 1 times 10 to the 5th pascals, plus rho, which is the density of water. The density of water is 1,000 kilograms per meter cubed. So that's 1,000 times G, 9.8, times the distance down, 0.6. So you'll get that the pressure is some number. After typing it into my calculator, I see that some number is 105,880 pascals. So you may wonder, why the heck would we want to find the pressure at the closed cap? And the answer is that in engineering any system ever with fluids, you got to know the pressure on all of your components to make sure they can hold up to that. So you could use this pressure, which equals force divided by area, to find the force that goes on this cap right here. You'd say that's pressure times the area of the cap. And that amount of force is going to be continuously railing against that cap. So you need to make sure your cap is securely enough on there to know if it will withstand that amount of force. So, for example, it may not have enough force to push it up at all, and you could just set the cap down and its own weight would be enough force there. Or it may be an extreme amount of force, so you need to weld the thing on. But you don't know until you calculate, and you've got to use pressure to do that. All right, this next slide is here as a set of problem-solving guidelines for these kinds of questions. We're just going to do a question together. I'm not going to read through these for you, but it is in the slides as a resource if you want it. All right, now we're going to look at this system. And this system looks crazy, but it's really not that bad. We've got two liquids here in the same tube. One of them is going to be oil. The orangish one is oil. The blue one is water. And the question is asking for the gauge pressure at the closed end, which is once again over here. So we need a problem-solving strategy here. We know that we can find the pressure at a depth. So we could find the pressure through this oil down to point A, and we could also find it to point P1. Now the hang up here that you might see is you might say that all points on the horizontal line are equal, so you could just find the pressure at A and apply it to pressure at P3, just like we did in the previous problem. The issue with that is that that only applies if you're looking at one fluid. If you've got a change in fluids, it doesn't apply anymore. So what we're going to have to do is find the pressure at P1, then say that's equal to the pressure at P2, make P2 the bottom pressure, the pressure at the depth, and make P3 that P sub naught in the equation to find it at the top. So I'm going to make this small so I have room to work. Starting with finding the pressure at P1. So for P1, I'm going to say pressure equals P sub naught, and then it's P sub naught plus rho. Sorry, that was a really poorly drawn rho. I'm going to redo it. Rho times G times D, which is the depth. All right, so that's just plug and play. Pressure at point 1 equals the pressure at the top, 1 atm, which is 1 times 10 to the 5th pascals, plus the density of oil. Now, side note, I haven't actually included those densities on this slide, but they are listed in a table in your homework. The density of oil is 900. Gravity is 9.8. And then the depth there is 75 centimeters, which is 0.75. So you type that into a calculator and you get some number for P1. And you should get 106,615 pascals. Now, in these questions, particularly because it's asking for gauge pressure, you're going to want to keep all of those units for now. All right, so we know that at point P2, the pressure is equal to P1 So it's the same number, 106,615 pascals. Now let's look at point 3. Point 3 is the top. So I'm going to write down our general equation again. Pressure, which is at the depth, equals the pressure at the top plus rho GD. This time around, we know the pressure at the depth, P2. So I'm going to make that this one, that's P2. The pressure at the top is P3. So this is going to be P3. We're solving for P3. Pressure at 2 is 106,615 pascals equals P3 plus rho. Rho for water is going to be 1,000. Gravity is 9.8. And the depth there is 25 centimeters or 0.25. If you type that in, solve it all out, you're going to get that your pressure 3 is 104,165 pascals. But this question asks for gauge pressure, so you got to subtract off 1 atmosphere, which is 1 times 10 to the 5th pascals, to get that your gauge pressure, 3, which I'm going to acknowledge as a prime, equals 4,165 pascals. All right, I hope this was helpful. Let me know if you got any questions. I'm going to try to have the buoyancy video up by 3rd block tomorrow. Sorry that I'm not producing these at a faster rate, but life's a little bit swampy right now, so doing the best I can.